down, sit down. Okay, let's see where we left off. Nomenclature and balancing equations.
Nomenclature?
Can anyone tell me what happens when a nonmetal and a metal are attracted to each other?
They form a relationship?
Yes, girl! Now what do we call this relationship? Naming binary ionic compounds is quite simple. Ionic means that the compound is formed between a nonmetal and a metal, and binary means that we're dealing with two atoms. So there are two types of ionic binary compounds. The first is where the charges or the oxidation numbers don't change, and then the second is where the oxidation numbers or charges do change. So first we're going to begin with those where there's only one charge. So as a general rule, we name the metal first, and when we name the metal, we use the name that it's given in the periodic table. So for example, Mg would be written as magnesium. This is followed by writing the nonmetal and giving it the suffix "ide." So let's take a look at some examples on the board. Given those general rules, how do we name NaCl? So first we would start with the metal. So we know the metal is Na, which is sodium on the periodic table. And the nonmetal is chlorine. So instead of writing the suffix "-ine", however, we're going to replace it and write the suffix "-ide". So it would become chloride. This makes the compound sodium chloride. Easy enough, right? So how would we write the compound given its name? So let's look at magnesium oxide. We know that magnesium is Mg, and that oxide is oxygen, so O. We also know that magnesium has a charge of +2 and oxygen has a charge of -2. So we could write the compound out as Mg2O2. This here and this here indicate the charges. However, we like to write things as simple as possible, so we'll cancel these out or reduce them and just write the compound as MgO. Okay, so calcium chloride is a little bit trickier, and it's only trickier because we're adding one more step. So using our general rules, we know that this compound, the metal is calcium, so Ca, and the nonmetal is chlorine, so Cl. However, this time their charges are not the same. So calcium has a charge of +2 and chlorine has a charge of -1. So what we're going to do is we're going to cross multiply these two charges. So what this means is that the chlorine is now going to have the charge of calcium, so +2, and the calcium is going to have the charge of the chlorine, so -1. So when we're writing this out, it's going to be calcium with 1 charge and chlorine with 2. So the final answer is going to be CaCl2. So what about the ionic binary compounds where there are multiple charges on the atoms? This occurs with most transition metals with the exception of zinc and silver. Well, the naming process is slightly different here. Since there are multiple charges on the ions, we need a way to distinguish what charge we're using. So there are two ways of doing this. The first is by using the stock method, which uses Roman numerals. It can also be referred to as IUPAC. Or the classical method, which uses two different suffixes to indicate the charge that they're using. So let's take a look at some of our examples here. So in Fe2O3, iron can have the charges of either +2 or +3, and oxygen has a charge of -2. So like we discovered before, we cross the charges of the two atoms when we're writing out the compound. So this means that iron in this case will have a charge of +3 since it's written beside the oxygen. So when naming this compound, you can write it in two different ways, like mentioned before. So first, let's look at the stock method. So the stock method uses Roman numerals to distinguish the charge of the multiply charged ion. This way also takes the general rules that we discussed earlier into consideration. So let's ignore the charges for just a second. How do we name this compound if iron didn't have two charges? It would be iron oxide, right? So we know that iron has a charge of +3, and we distinguish this by writing iron 3 oxide, with the charge written in the brackets and in Roman numerals. So the second way of writing this is the classical method. So this way gives the metal a prefix to distinguish the charge. These prefixes correspond to the size of the charge. So by using the prefix "ik," it indicates a higher oxidation number or a higher charge, and by giving it the prefix "us," it indicates a lower oxidation number. So in this case, Fe2O3, we know that iron has the higher charge, so this will be indicated by using the suffix "ik." So it'll be ferric oxide. And we remember that oxide has this IDE because it's the nonmetal, and that's the suffix that we give it as we learned earlier. So looking at the second example, iron 3 chloride, we know that iron is Fe and chloride is chlorine, so Cl. So given the Roman numerals in the brackets, we know that the charge of iron is going to be +3, and we know that chlorine has a charge of -1. So as we learned earlier, we cross-multiply these two charges when naming the compound, so chlorine's going to get the 3 and iron's going to get the 1. So when we're finally naming the compound, it's going to turn into FeCl3 as our final answer.
Shut up! This isn't hard. My dog could do it in his sleep.
Okay, sorry, so what's next?
Next, we have another type of ionic compound with polyatomic ions.
Ionic compounds can be formed between a metal and a polyatomic ion. Earlier we discovered that binary compounds consist of 2 atoms. Well, polyatomic ions are going to consist of many atoms, usually 3. So when it comes to naming ionic compounds, the equation sheet handed out will be your best friend. The general rule for naming these types of compounds is first you name the metal using the name that's given in the periodic table, so Mg would be magnesium, and this is followed by naming the polyatomic ion. Very simple. So looking at our first example, LiSO4, following the general rules, you would name the metal first, so Li is lithium, followed by naming the polyatomic ion. So this is the polyatomic ion. Looking at your equation sheet, it is sulfate. So this entire compound is called lithium sulfate. So the next example is a little bit trickier, copper 2 sulfate. So remember that copper is a transition metal, meaning that it has more than one charge. So this example is written using the stock system, and it indicates that copper has a charge of 2, so it's going to be +2, because it's written in the brackets using Roman numerals. So looking at the equation sheet, we'll learn that sulfate has a charge of 2-. So if we were to write this out, it would be copper, so Cu, and the polyatomic ion, so SO4 with its 2 charges. So when you cross multiply, so 2, and then it'll be 2 here. So we put the brackets around the SO4 to indicate that this charge of 2 applies to the whole polyatomic ion and not just the individual atoms inside. Wait a minute though, something doesn't exactly look right. So there are 2 2's here, so they should be able to cancel out. Remember that we like to write things in the simplest and most reduced form. So that means that Cu2SO4 will actually be written out as CuSO4 as the final compound. You may be wondering why in the second last example we used ferric and not ironic. Well, there's always a specific way of writing things in chemistry. There are certain elements that when naming it using the classical system, their Latin or Greek names are preferred. Here's a list of them that is highly recommended to memorize. Feel free to pause the video and copy them down. And one last thing that should be noted is that the stock method is always preferred to the classical method.
Okay, so ionic binary done, polyatomic done.
Okay, so what about nonmetals and nonmetal compounds?
Oh yeah, those are called covalent compounds.
Wow, you finally got something! Non-metal and metal form covalent compounds!
Simple covalent compounds consist of a nonmetal and a nonmetal, and the nomenclature for this is actually quite simple. So the first way we can name simple covalent compounds is using the stock method with Roman numerals that we saw earlier on. So if you look at our first example, FeO, we will take the name of the first nonmetal, iron, plus the second oxygen with the suffix I, just like we did with ionic compounds. Now, to find the charge on iron, we know that the two possible charges are +2 or +3. We'll use the cross multiplication technique as we did earlier on. We know the charge for oxygen is -2, so that means the charge for iron must be +2, and we write that in Roman numerals, so we get iron 2 oxide. Now, if you look at our second example, we'll take the first nonmetal again, gold, plus the second, nitrogen with the suffix "ide," nitride. And we know that nitrogen has a charge of -3, so that must mean that gold has a charge of +1, and we get gold 1 nitride. Now for our last example, carbon chloride, we'll write that in CCl. We know that chlorine has a charge of -1, so that must mean that carbon will have a charge of +4. So that gives us CCl4. The second way we can name simple covalent compounds is using Greek prefixes. So to do this, it looks quite complicated, but it's actually, again, very simple. Here is a table of prefixes in Greek that it's important to memorize. So here we have the number of atoms of each element and the Greek prefix that goes along with it. So how we name this is we start with the Greek prefix of the first nonmetal, then we have the Greek prefix of the second nonmetal, and we add it again to the suffix "ide." It's important to remember that if the Greek prefix for the first nonmetal is mono, as in there's only one, we don't need to include that. So for example, if we have CO, this would be called carbon monoxide, which I'm sure we're all familiar with. So there's no need to add a mono to this carbon, just to the second one. All right, so if we're going to look at some examples, here we have N2O5. So to name this, we'll look at the 2 and add a Greek prefix for that. So that would be di, looking at our chart here. Then we put the first nonmetal, dinitrogen. And then we'll take the Greek prefix for the second one, 5, so that is penta. And then we take the second nonmetal, which is oxygen, and add the suffix "ide," pentaoxide. So we get dinitrogen pentaoxide. Now for the second one, this is H2O, which is we all know as water, which can be also called, if we take again, first the Greek prefix, that's di, and then the first nonmetal, hydrogen. And then this one is just a 1 here, so it's mono. And then the second nonmetal, which is oxygen, and add the suffix "ide." So we have monoxide, dihydrogen monoxide.
Oh, I think I'm finally understanding now.
Okay, now time for another covalent compound, binary acids.
Oh, never mind.
Another type of covalent compound is a binary acid, which consists of a hydrogen and a nonmetal. And the nomenclature for this is very, very simple as well. So how we name this is we start with the prefix always of hydro, add the name of the nonmetal and the suffix "ic, and then add acid at the end. So here for our first example, HCl, we're going to take the prefix hydro and the name of the nonmetal, chlorine, with the suffix "ic," so chloric, and then simply add acid. So we have hydrochloric acid. We'll do that again for a second example, which is H2S. We'll add hydro, and then the name of the nonmetal, which is sulfur, with the suffix "ic," so sulfuric, and then acid. So we have hydrosulfuric acid.
All right, next we have hydrates, which is a non-metal and a metal or a polyatomic ion mixed with water. Speaking of water, this weekend I went golfing and the bloody golf ball rolled into the water even though I had the perfect swing. Oh, where's Adam today? He would understand.
Wait, should we be taking notes on this?
No, put your pencils down and listen. Now, hydrates.
So a hydrate consists of a metal, a nonmetal or polyatomic ion, and water, H2O. So to name a hydrate, first you name the ionic compound in the first part of the hydrate, which we learned earlier on. Then you add the Greek prefix for the number of H2O molecules, and then the suffix hydrate. So here, if we look at our first example, we have CaCl2, 2H2O. So first we're going to name this ionic compound, which we know is calcium chloride. And here we're going to find the Greek prefix since there are 2 water molecules. If we remember back to our table of Greek prefixes, we know that 2 is di, and then we add the suffix hydrate. So we call this calcium chloride dihydrate. So now if we look at our second example, BaOH2, 8H2O. Here is an ionic compound example where we have a metal and a polyatomic ion. So like we learned earlier on how to name this, this is barium hydroxide. And then for our Greek prefix, we see that we have 8 molecules of water. We know that 8 is the prefix octahydrate. So that gives us barium hydroxide octahydrate.
Now if you think that was hard, our last type of compound, Oxy Acids, is tricky. No, girls, I told you to put those pencils down. Listen up!
Now on to naming oxy acids. What exactly are oxy acids? Well, they are aqueous solutions of compounds containing hydrogen, oxygen, and a third element. Here's an example. H2SO4 aqueous. The third element is sulfur. Oxy acids are named from the polyatomic ion. So in SO4, we use sulfate. In NO3, we use nitrate, and in PO3, we use phosphite. Now with naming the oxy acids, if the polyatomic ion ends in 8, we use the root of the third element and add an ic and an acid. Here's an example. In HNO3, NO3 is our polyatomic ion, nitrate, which ends in 8. Therefore, we are going to add ic, which then becomes nitric acid. However, if the polyatomic ion ends in ite, we use the root of the third element and add us and acid. Let's do an example. In HNO2, our polyatomic ion is NO2, and it is nitrite. Therefore, we add us, and it becomes nitrous acid. Now let's go over some more examples. In H2SO4, the polyatomic ion is sulfate. Therefore, following the rules, we add ic and name it sulfuric acid. In H2SO3, the polyatomic ion is sulfite. Therefore, it becomes sulfurous acid. Now here's a quick summary. When naming, we need to use the polyatomic ion, and if the ending ends in 8, we add ic and acid, and if the ending ends in ite, we add us and acid.
Okay, oxy acids, done. Oh, we still have 2 minutes left. Plenty of time to go over balancing equations. Balancing equations is a lot like cooking. I don't cook, but my cook tells me it's a lot like baking. You have the same amount of things that you put in, but then the product will have the same amount of ingredients but rearranged.
Now on to balancing chemical equations. We need to ask ourselves, what exactly is a chemical reaction? In a reaction, atoms are neither created or destroyed. So in a chemical equation, they must have an equal number of each type of atom on both sides of the reaction arrow. So we need to start off by balancing those elements that occur in only one compound on each side of the equation. Now, one thing that's really important to remember is that when balancing chemical equations, you can only change the coefficients while balancing chemical reactions, never the subscripts. If you change the subscript, you're changing the identity of the compound. Now let's take a look at an example. Before we begin, we may want to take an inventory of how many of each type of atom are on each side of our reaction arrow. On the reactant side, we have 1 carbon atom, 4 hydrogen atoms, and 2 chlorine atoms. On the product side, we have 1 carbon atom, 5 chlorine atoms, and 1 hydrogen atom. Now, because we have 1 carbon atom on the reactant side and 1 carbon on the product side, carbon is already balanced. Our next step would be to balance the hydrogen atoms. In order to balance the number of atoms of hydrogen on the product side, we need to add a coefficient of 4 in front of HCl. Now, if we count up the amount of atoms we have on both sides, you'll see that we still have 1 carbon atom on both the reactant and product side. But since we now have an increased amount of hydrogen atoms on the product side, we now have 4 hydrogen atoms and a total of 8 chlorine atoms. 4 from the 4Cl4 to begin with, and our 4 molecules of HCl. Now, if we compare the number of atoms we have on the reactant side and product side, we only have 2 chlorine atoms on the reactant side. So in order to balance our chlorine, we need to add a 4 coefficient in front of Cl2. That means we now have 8 atoms of chlorine on our reactant side. Now let's take a look at another example. NH3 plus CuO. Here we have 1 nitrogen atom, 3 hydrogen atoms, and 1 copper atom and 1 oxygen atom on the reactant side. On the product side, we have 2 nitrogen atoms, 2 hydrogen atoms, and 1 copper atom and 1 oxygen atom. First off, we're going to focus on oxygen and hydrogen. The oxygens are balanced, but the hydrogen are not. We can solve this by doing crisscross multiplication to get 6. We're going to multiply NH3 by 2 and NH2 by 3. This will give us 6 hydrogen and 2 nitrogens. And over here, it is going to give us 6 hydrogens and 3 oxygens. Now we will need to balance the oxygen. We're going to multiply CuO by 3 and get 3 oxygens, but we are also going to get 3 copper. There's still a problem with copper. We can add 3 in front of copper. This whole equation is now balanced. One thing to take note of when balancing equations is that first we need to balance the metals, balance the nonmetals, and then balance the hydrogen and then the oxygen. And there you have it. You've mastered balancing equations.
Alright, everything done.
Wow, that's pretty easy.
That's because I'm a goddess. Now get out of my class.
First things first, rest in peace, Uncle Phil.